Hello and welcome. We live in a world that feels pretty random and uncertain a lot of the time. But what if I told you there's a whole branch of math designed to make sense of all that chaos? Well, there is. It's called probability, and in this explainer, we're going to break down exactly how it works.
Think about how many times you've asked this question. What are the odds it's going to rain? Seriously, what are the odds my team can actually pull this off? What are the odds I land that job? It's maybe the most human question there is when we're staring into an unknown future.
And it turns out, every single time you ask that, you're tapping into the core idea of probability. So let's look at this as a journey, like we're climbing a ladder. And by the end, you'll know how to answer that question with the power of math. Okay, so let's start at the very bottom, the ground floor. Before we get into the how, let's talk about the why. Why do we even need this stuff? Well, the short answer is, the world is unpredictable. Things are messy, and we need a tool to measure that messiness, to actually put a number on uncertainty itself. And for all its power, probability at its core is incredibly simple. It's just a number that lives on a scale from 0 to 1. 0 means something is absolutely impossible. It's never ever going to happen. 1 means it's a sure thing. It's certain. And everything else, all the maybes of life, they just fall somewhere in between. But don't let that simplicity fool you. That simple 0 to 1 scale is the engine humming under the hood of our modern world. Seriously, it's driving the algorithms in machine learning. It's in the models banks use to handle risk. Probability is the invisible architecture holding up so much of our technology and decision-making. All right, let's take our first step up the ladder. To really speak the language of probability, we just need to know a few key words. And I promise, it's way simpler than you might think.
First word, experiment. Now, forget the lab coats and bubbling beakers. In probability, an experiment is just any action where you don't know the exact result beforehand. Flipping a coin? That's an experiment. Rolling a die? Yep, that's an experiment. Watching to see if a customer clicks on an online ad? You guessed it, that's an experiment too.
So every experiment has potential outcomes, and an outcome is just what it sounds like. It's one specific thing that can happen. You flip a coin, you get heads. That's an outcome. The customer clicks the ad. That's another outcome. It's really that straightforward. And finally, what if you list out every single possible thing that could happen in an experiment? Well, that complete list is what we call the sample space. Think of it like the entire menu of possibilities. For that coin toss, the menu is pretty short. Just heads and tails. For a 6-sided die, the menu has 6 items, 1, 2, 3, 4, 5, and 6. Now this is where it gets interesting. There are really 2 main ways to think about where these probability numbers come from. On the one hand, you have the classical approach. This is pure theory. We just know a fair die has 6 sides, so the chance of getting any one of them has got to be 1 in 6. But on the other hand, you have the empirical approach, which is all about real-world data. We can't use pure theory for the weather, but we can look back and say, well, it rained on 90 of the last 365 days. That gives us an educated guess based on what we've seen happen. Okay, time to climb up to the second rung. We've got the basic vocabulary down, so now we can start to see how different events relate to each other. And trust me, this is where probability really starts to show its power. So there are 3 main ways that events can interact. First, they can be independent, which means one event just doesn't care what the other one does. Getting heads on a coin flip has 0 effect on the next flip. Second, they can be dependent. This is like drawing cards from a deck. If you pull out an ace and keep it, the chances of getting another ace have just changed. And finally, events can be mutually exclusive. This just means they can't both happen at the same time. You can't get both heads and tails on one flip. It's one or the other. And all of this leads us to one of the biggest ideas in all of statistics, conditional probability. It sounds fancy, but the idea is simple. It's just asking, what's the probability of something happening given that we already know something else happened? It's all about updating our beliefs as new information rolls in. And this is why it is so important. That little phrase, given that, is doing some serious heavy lifting in the real world. It's at the very heart of medical diagnoses, it's what drives online marketing, and it's how weather forecasting works. That given part is the new evidence that lets us make much smarter predictions. So, we've gone from the basic words to how events interact with each other. Now we're reaching the third rung of the ladder, and this is where we find the real game changers, the big theorems that turn all these concepts into incredible power tools. And let's start with a big one. A tool so important, it's often called the engine of modern AI and machine learning. I'm talking about Bayes' theorem. Now, don't worry about the complex formula for a second. Just focus on the idea. Bayes' theorem is basically a mathematical recipe for learning. It tells you exactly how you should update your beliefs when you get new information. You start with what you think is true, your prior belief, you get some new evidence, and the theorem gives you your new, updated belief. This is the logic that powers everything from your email spam filter to Netflix's recommendation engine.
Next up, we've got a tool with a name that says it all, the law of large numbers. It's a really simple but profound idea. All it says is that the more times you do something, the closer your actual results will get to what you'd expect in theory. This is literally why casinos know they'll make money in the long run, even if they lose a few hands. Randomness eventually evens out. And finally, we have what some people call the most important idea in statistics, the central limit theorem. And it honestly feels like magic. Here's what it says. You can take almost any random process, no matter how chaotic, and if you start taking the average of small samples from it, a beautiful, predictable pattern emerges from the noise, the classic bell curve. It's how we find order in chaos, and it's the foundation for so much of how we test ideas with data. Okay, we've made it. We're at the top of the ladder. Now we can look down and see how all of these pieces, from that simple 0 to 1 scale all the way up to these powerful theorems, actually come together to shape the world around us. Just look at the tech you use every single day. The spam filter that keeps your inbox clean, that's Bayes' theorem deciding the probability that an email is junk. When Amazon recommends a product, it's calculating the probability you'll like it based on what other people have done. This isn't just theory. It's running on your screen right now. And it's way beyond your computer, too. When a doctor interprets a test result, they're using conditional probability. When a financial firm models stock market risk, that's probability. The weather forecast literally gives you the probability of precipitation. It is the mathematical language of risk, and it helps us make smarter choices in almost every field imaginable. But this brings us to one last really fascinating question. If this mathematical system is so logical and so powerful, why are our brains so, well, bad at it? The answer is that our intuition has some serious bugs when it comes to chance. Our brains are hardwired to find patterns, even when we're just looking at random noise. We see a coincidence and we immediately think it's causation. We are terrible at intuitively grasping the real odds of rare events, and we get completely twisted around by conditional probabilities. The simple truth is, our gut feeling is often just mathematically wrong.
And that, right there, is why this all matters so much. We need a formal system like probability, precisely because it helps us overcome our own flawed thinking. It gives us a rigorous, dependable way to think about uncertainty. It's the tool that lets us look at a messy, chaotic, random world and transform it into something we can measure, understand, and act on. It transforms randomness into knowledge.